Hello, I'm going to just go through one more example looking at z-scores and standardization. This idea of standardization, um, I think it's important. In teaching this class, I find students sometimes struggle with this idea, so I want to look at maybe a more concrete example. This will kind of make this all make sense. I've got three variations of the z-score formula. Z equals your data value minus the mean over the standard deviation. So this first value would be like if you're looking at population. Or we could let z equal x minus x bar over s if you're just comparing to sample data. Or if we're doing a hypothesis test, we're thinking about z is equaling your statistic minus the null value over your standard error. All these are roughly the same idea. Your data minus some assumption or something you already know, and then divided by your variability, your spread. Okay, so I'm about 6'2". My wife is 5'11". We're going to assume, I Googled this last semester, that in the US, recent studies have shown that the average height of men is 69.1 inches and a standard deviation of 2.9 inches. The average height of woman is 63.7 inches with a standard deviation of 2.7. That should also be in inches. And we're going to assume the distribution of heights for males and for females is normal. We're going to assume a normal distribution. All right, so let's see, fix my typo. Who is taller, me or my wife, relative to our sex, male versus female? Obviously, we said pure data. I am about 3 inches taller than my wife, but she's pretty tall, 5'11". So we want to bring in the idea of, well, what's the average height versus the spread, the variability. So let's see, I'm going to change this color here. We need to calculate both of our z-scores to determine who is taller relatively. So I'll say z me. All right, my height is 60. Oh, wait, sorry, I'm 6'2". So that's 6 times 12 inches per foot, and then plus 2. So I am 74 inches tall, and then minus the average height, we're going to take this assumption, 69.1 inches tall, and then divide that by the variability, the spread of US men's heights to be 2.9. So I'm going to throw this in my calculator. And I'm going to round this to 3 decimals, is approximately 1.6896. So 1.690, around 3 decimals. So I am 1.69 standard deviations above the mean. That's what that number represents. But if we calculate the z-score for my wife, she is 5'11". That's 1 inch less than 6 feet. And 6 feet is 72 inches. So she's 71 inches tall. Minus her population height is 63.7. And that divided by 2.7. 71 minus 63.7. And then divide that by 2.7. In the calculator, I got 2.704. So that means my wife is almost 3, 2.704 standard deviations above the mean. So this means my wife is much taller relative to sex. Right? The idea is the z-score puts our two heights on the same scale. When we're looking at z-scores, we're on the same scale now. So I can compare myself to my wife relative to our two groups, even though men are about 5.5 inches, 5.4 inches taller on average, And there's a little bit more of a spread of heights for men, but pretty close. The standard deviations are pretty close. All right, the next thing I want to look at is what percentage of men are as tall as Professor Melvin. So I'm looking at what portion or percentage of men are 6'2" and taller. So I'm looking at 74 inches and taller. And if we assume the distribution for heights for males and females is normal, I want to show you two different ways to get this answer. Both, you need to go to Stat Key or Normal Calculator. I'm going to go to Stat Key. Click on the normal for normal distribution. And I have two options. I could just look at my z-score. So we could use my z-score of 1.69 and the normal distribution centered around 0, standard deviation 1. To get click on right tail because I want to know the proportion of people that are my height or taller, and I need to change this bottom entry. This is the z-scores down here to 1.69. So if we assume a normal distribution, this is saying about 4.6% of the population is my height or taller. 4.6% of U.S. men are 6'2" or taller. Or we could use the normal distribution. We can use my height is x equals 74 inches and the normal distribution. But now I want to use the population distribution as 69.1 and standard deviation is 2.9. To get, go back to the normal distribution, edit parameters, change that middle to 69.1, and the standard deviation is 2.9. So here, the center of this will be about that 69.1. Right tail, and I need to change this bottom entry to 74. And voila, we get the exact same thing, 4.6%. All right, so for my wife's height, let's just use the z-score. So I'm going to use her z-score is, 2.704. If I use z-score, and I need to go back to the standard normal distribution where the center is 0 and the standard deviation is 1. So add parameters, make that mean 0, standard deviation is 1. Click on OK. And now I'm going to click on right tail. And this bottom entry is that 2.704. Click OK. Notice that is the percentage, 0.0034. Which is the same thing as 0.34% of U.S. women are 5'11" or taller. So for me, it's almost 5% of U.S. men are my height or taller. For my wife, it's less than 0.5% of U.S. women are taller. And this is why I generally could find clothing that fits me at most stores, and my wife has to do more special ordering and custom stuff. She's at much more of an extreme end of the tail than I am. So here's my wife. She's much farther away, and I am the 1.69 z-score, much closer to the actual center. All right, I hope this helps kind of get the idea of the standardization. It could put different groups that have totally different, population means and standard deviations on the same scale. And if we assume distributions are normal, we could use that to get percentages.